Now, again, I think that there are a couple of people who haven't been in one of my workshops before. So we start every exam question by highlighting important bits. So we can see we're looking at the escape speed, and we're starting with mass m, radius r, and speed v. What's the escape speed if I double the mass and halve the radius? Okay, so for every question, as soon as I see a word that links to an equation, I'm going to write it out. So from the data booklet, I know that the escape speed is equal to the square root of 2gm over r. Okay. So for my first one, I'm going to label all of these 1, just so it's clear which one I'm talking about. So v1 is equal to the square root of 2gm1 over r1. Now let's go for a different color. And these are all mass 2 and radius 2. So this is m2, this is r2. So v2 is equal to 2g m2 over r2. What I can do is I can replace these with the expressions I've got here. So this is in terms of m1, and this is in terms of r1. So that's equal to the square root of 2g, and then we got times 2m1 over r1 over 2. So that's equal to the square root of 4 times 2gm1 over r1. Now, the key thing about surds, and I think we looked at this a little bit last time, if I've got a multiply inside the surd, what I can do is I can split along the multiply. So we can split across the cross. So that becomes the square root of 4 times the square root of g m1 over r1. Square root of 4 is 2. And this expression here is v1. So I can see from working this through that the answer is going to be C. Okay. Now, what you could have done to maybe think about a quicker method, if I just look at the equation, I can see that increasing the mass is going to increase the speed, and decreasing the velocity is going to increase the speed as well. So I could have ruled out A and B as well, because I knew V had to increase. And then it's between C and D. And if you sort of, again, we're thinking about a quick method, well, remembering that I've had a factor of 2 change for both of them, so it's an overall factor of 4, but I've got to square root anything, so it's going to be 2. My method, I mean, I still think I managed to answer it just about in 1.5 minutes. So this kind of method I think is better because it's also appropriate for paper 2 if it's worth 2 or 3 marks. But of course, ruling out silly answers is always a useful approach to take. So for the second question, I've got a gravitational field to the surface of a planet is uniform. We've got the gravitational potential difference. So I'm already thinking, okay, I need the gravitational potential equation between the surface and a point 30 meters above is 15 joules per kilogram. What is the work done in raising a mass of 4 kilograms from the surface to a point 10 meters above? And then we're told the gravitational field close to the planet is uniform. Okay, so let's have a think. Well, the gravitational potential difference, so delta V is equal to 15 joules per kilogram. And I have in my data booklet that the work is equal to the mass times delta V. But the thing to be careful about here is that I'm using a point 10 meters above, not 30 meters above. So if at 30 meters, delta V is equal to 15 joules per kilogram, If I'm told that the gravitational field is uniform or constant, it means that if I just take a third of my distance, the potential is only going to change by a third. Okay, so the change in potential is 5. So now the work is going to be 4 kilograms times 5. So that's going to be 20 joules. Okay. Now, so that's the 2 short questions. So again, on this one, I picked the equation that is most relevant because I needed work and I've got the mass and the change in potential. But I needed to adjust my change in potential because I'm not using the full 30 meters. I'm using just a change in 10 meters. Now we're going to look at some of the longer questions. So the table gives the gravitational potential for various distances r from the surface, show that the data are consistent with the Earth acting as a point mass. So what I'd expect then is that V should equal minus gm over r. So, and then if it's acting as a point mass, then r should equal the distance r from the surface plus the radius of the Earth. Okay, so the method I would do for this one here is I would take each r. So we've got the data, which was 0, 4, and 32. I would so that was little r. Then I want big R equals r plus the radius of the Earth. So that's going to be 6.4 times 10 to the 3, 10.4 times 10 to the 3, and 38.4 times 10 to the 3. And then if I know all the radius, what I would do is I would find my own versions of the gravitational potential. So calculate V yourself for each radius. So for example, for the first one, V is equal to minus the gravitational constant, I think is 6.67 times 10 to the minus 11. Someone correct me if I'm wrong for that one. Times the mass of the Earth, which I don't know, over the value of r. So 6.4 times 10 to the 3. So the answer I get for this one is going to be so I get 1.04 minus 1.04 times 10 to the minus 14. And so because I know what the potential is, I can find the mass of the Earth is equal to, oh, sorry, I keep clicking the wrong way. Minus 6.24 times 10 to the 7 over minus 1.04 times 10 to the minus 14 equals 5.99 times 10 to the 21 kg. And then use this m to check the other potentials. Okay. So whenever you're asked to sort of confirm values or show that things are consistent, the best thing to do is to use one piece of data to get the unknown. So this was the unknown. So find this first using the data, and then use it to obtain correct results for other data. So if I take that value and then use it with the data for the next answer, so dividing by 10.4 10 to the 3, I get minus 384 and then 5 zeros, which is the exact same answer I got here. Okay. Now, finally, a separate question. Do we have enough time? Just about. So we've got two stars orbiting around a common center. The mass of each star is m and the separation is 2r, the speed is v. Well, let's look at the forces that are going on here. So the centripetal force uses this as the center. So it's going to be the mass of each star, so m, times the velocity squared divided by the radius. But for this one, the gravitational force, so Fg, is equal to gmm over, now remember for the gravitational force, it's the separation between objects. So this is going to be 2r squared. So capital Gmm over 4r squared. Okay, so the reason this is just 1r is because the centripetal is always to the center of the circle. And then the gravitational force is always between the objects. So I'm expecting that this is going to come up in the question we're going to get asked. Find the velocity of the orbit. So remember when we're doing the velocity of the orbit, we equate the centripetal force to the gravitational. So I get that mv squared over big R is equal to gmm over 4r squared. And similarly to when we did the derivation ourselves, we can cancel one of the r's and we can get rid of the m. Square root both sides. So I get that little v is equal to the square root of gm over 4r. Now the thing about when you're given so that, it means that even if you can't find this answer yourself, you can always use it in the next question. So then we're asked for the period of the revolution. So we're told that the v is equal to gm over 4r square rooted. And for a circle, the velocity is equal to 2 pi, the distance traveled, 2 pi r, sorry, the distance traveled, divided by the time, which is the period. So now I need to rearrange this to make the period the subject. So square both sides to get 4 pi squared r squared over t squared is equal to gm over 4r. Take t squared up to the top and 4r up to the top on the other side, gm onto the bottom. So I get t squared is equal to 16 pi squared r cubed over gm. So t is equal to the square root of all of that. Okay, so all we did here was said that the velocity is distance over the time and rearranged it to make time the subject. Okay.